All right, so I want to start today's class. In terms of where we are in the grand scheme of things, so we've gone through what good quant research looks like, research design looks like. We talked about surveying and some guidelines around that. We talked about descriptive statistics, the last two classes, session 3 and session 4. We're going to move into a different type of statistics. So today what we're going to look at is how do we compare indicators. Today is numerical, and then next class will be categorical. And these are called inferential statistics. So we're leaving behind descriptive and we're moving into inferential, where you can draw inferences. And I'll explain what all of that means in just a moment. So some of my goals for today: to explore inferential statistics, to get your toes wet in that, to learn to identify when differences between continuous groups are real, to learn to identify when two continuous indicators are related to one another. So there are two tests. Each of them has its own test. To learn how to use Excel to calculate those two tests. So they're called t-tests and correlations. And to practice using real world examples. Have any of you heard, I would imagine you've heard of correlations, right? How about t-tests? Have any of you heard of that? Okay. Okay, so we'll go through what that is and why you would use it. And we'll actually start with t-tests.
And correlation is different from regression.
Yes, it is. Very similar. And it's really funny because Simeon was just asking me that question, like where is the distinction? I'll make sure that next class I pull in and distinguish what each of those means. It's a little different. Okay, so in terms of concepts that we've gone over that I just want to hit upon again, because we'll be building on them. The first one is the difference between population and sample. This is a slide from last class, but just a reminder that the population is absolutely everybody that you want to study. And then a sample is a carefully selected group of people from within that population. And the point here is that it's the central limit theorem that enables you to take the conclusions from the sample and to generalize to the population. So I know you were learning about the central limit theorem. You watched that video hopefully more than once to just get an understanding of what that means. But we're going to touch upon that a little bit now today. But before we begin, when it comes to the well-being study, are we talking about population or are we talking about sample? Why do you say that?
Because it takes only the proportion of the sample in New York and their well-being, not the whole population.
Yeah, good. People agree. I see head nods. Does anybody think it's population?
The population of New York?
Yeah. Well, I mean, that's a really good point, is what's the context that we're speaking of.
Right.
And so we want to generalize to all of New York. So when we're looking at complaint data, for instance, is that population data or is it sample data? Is my question. It's sample. Yeah, you're absolutely right. And for just that reason, it's a select group of people. Granted, they opted in. It's not like we carefully selected each of them, but it's still sample. It's not the whole population. Okay. So then the next concept I want to make sure that we can iron out and distinguish between, and that's what numerical versus categorical is. Is anybody familiar with that distinction? Like, does anybody feel confident explaining what that means? Some difference between the two.
Categorical, for example, if you say, you give 4 options like yes, no, maybe, likely, that's categorical.
Yeah.
But if numerical is when it is basically a specific numbers.
Yes, perfect. Yep, exactly. Numerical, they're variables. They can have multiple to infinite values. They have a logical and incremental order. So some examples are date and time, the count of participants, age, height. They're actual numbers and they relate to each other in a certain way. Whereas categorical is a finite list. They're often subgroups and they don't necessarily have a logical order. So an example might be borough, right? That doesn't really necessarily have an order. We might put it in alphabetical order, but they don't need to be in a certain order. There's no logic to it. It is usually text, but we can code it, right? Like Bronx, we could say is 1, Brooklyn 2. But if we code it into numbers, those numbers have no real value. Just because Brooklyn is 2 and Bronx is 1 doesn't mean Brooklyn is greater than Bronx. So similarly with gender, zip code can be confusing because it seems like it's numerical because it's numbers, but again, it doesn't really have a value. It doesn't show any relation to the others. It's just a categorical number. So that's important because when we're choosing different statistical tests, we have to know what type of number we're looking at, and that helps you to choose. And so really that's the short, it's the short answer to whether you use correlation or regression. It depends on what type of numbers we're working with. So today we're going to be focusing on numerical numbers. Next class, like I said, will be categorical. Yeah.
Go back about the zip code. Why is it that? Because it's not infinite number?
Correct. Yep. It doesn't go on forever. It's always just 5 digits, or I guess if you add, 4 digits after the hyphen, it would be 9, but never more than that. And again, if your zip code 10001, it doesn't mean you're greater or less than 10002. It has no relation to each other. It's just a code. Make sense?
The relation is not really.
So here's another way to tell. No, it's okay. Another way to tell is, would it make sense to do math off of it? So would it make sense to do an average of zip codes? Like if you had a list of zip codes, would it be helpful to have the average of them? Not really. It wouldn't tell you anything. And that's a hint at the fact that it's categorical. When you have numerical, it will mean something. So if you have a list of dates and you were to get the average date, it would tell you the average time that whatever happened. Okay, so we're focusing on numerical today. And then, like I said, if you have sample data, it's the central limit theorem that enables you to take that information and generalize to the whole public. So just to go over what that is, it's a theory that states no matter the distribution pattern of a population, a large number of properly drawn samples from the population have means that are normally distributed around the population mean. Anytime I read that,
How did you find these things? How did you do it?
So if I were to summarize it in layman's terms, it's a natural phenomenon. So that's worth knowing that it's a thing that repeatedly happens in nature. And it says that the average of a population's samples fall along a bell curve. And the variation grows closer to the mean the larger the sample size. So that's why we always look for that large sample size, because you're getting closer to the average, the population average. And this allows us to conduct inferential statistics. So basically, I love the example with the rabbits in that video. I think that does a really nice job. But basically what it's saying is if you choose large enough samples, they all get distributed somewhere in here, but the largest cluster is going to be right around here. Its mean, the sample's means, are going to be very close to the population mean. So our chance is if we picked one sample, it's most likely to be right around here. It's very likely that it will be aligned. Its statistics will be aligned with the population statistics, which is why you're able to generalize to the population. So what does that mean for evaluators?
Does that mean it's a normal distribution? What if it's not a normal distribution?
So, and that's what the really cool, the natural phenomenon is that even if, and the example was dragon wings, I think, even if a population does not have an even distribution, it's abnormal. If you were to sample it a proper number of times with a large enough sample, it will fall along this natural distribution.
It's so weird.
It's really crazy.
Yeah.
It's really crazy. And like, it hurts my brain a little bit still to think about, but in the end, like if you can explain it or not, what's important is that you know what that means for us. which is that we don't have to collect data from the entire population. That's the bottom line. And we can trust that if we properly draw a sample, we can generalize to the whole public.
So if you have an inverted bell, if you have a large enough data set, it will fall under the inverted bell.
It will fall under the proper bell. It won't be inverted anymore. It's the craziest thing. It's the craziest thing. And it's one of those, like, yeah, you trust the mathematicians before us that that's the case. So because of the central limit theorem, we're able to do these statistics that we're about to explore. We'll explore 4 or 5 different types, and they're all called inferential statistics. And what that only means is that we're inferring things about the general population based on our sample. So the inferential statistics is the second of 2 main types of methods. It helps us to draw conclusions that extend beyond the immediate data. It helps us to generalize from the sample to the general population. It also helps us to see if there are relationships within the data. So I like to think of it as within the columns. So we can look within one data set, or we can compare multiple data sets to each other. It's only intended to be used on sample data. There's one exception, and that's correlation. And we'll talk about what that means. And it's made possible by the central limit theorem. So in general, and I say it's only intended to be used on sample data, you wouldn't use it on population data because it's not necessary, right? Like, you already have all the data you need. You don't need to do any inferring. So you really only use it when you have sample data. Okay, so there are 2 main statistical methods. We talked about the descriptive statistics. These are all the things that we talked about in the last 2 classes. And then inferential, here's a list of the most popular ones. There's t-test ANOVA, MANOVA, which is very related to ANOVA, chi-square, regressions, and correlations. So we'll be talking about all but the regressions. But like I said, I'll make sure I fold that into next class, just so you can see where it fits with the others. And mainly we'll be focusing on ANOVA, but I can tell you what MANOVA means similarly next class. Today, what we'll be talking about is the first and last, t-test and Pearson's correlation. So our first research question that I want to talk about, how do we answer this, is how do I compare one group of people to another? And this test will enable us to do that, and it's called the t-test. So the t-test, it assesses whether the difference between the means of 2 groups is significantly different or not. So as evaluators, that's helpful to us if we're ahead of evaluation, like if we're doing work before an evaluation, we want to identify if 2 groups are similar. So if we're doing some sort of either randomized control trial or even quasi-experimental, and we want to find these 2 groups that are equal in every other way, that would be the test that we would use. And then similarly, post-study, if we want to determine if a group is significantly different after the intervention. So you might run a t-test before to look at them, and then afterwards to compare them and see if there's a difference. And then another time might be if we want to determine if 2 indicators are significantly different. So within a data set, if the men have a different outcome than the women. It's another way of just comparing among 2 groups. So in Excel, well, first of all, does that make sense? Kind of on board with me? All right. So in Excel, there are 2 different types of t-tests. The first one is the independent samples t-test. I would say that's the most commonly used. And this compares the means of 2 different groups. So they are different, but we want to see if there is any significant difference between the 2. So in Excel, it's called the 2-sample t-test, assuming either equal variance or unequal variance. You'll see both of those in the data analysis options, and we'll look at both of them. Now that contrasts with the paired sample t-test. So this is like what you might do with pre-test, post-test. These are exactly the same people, and you want to compare their outcomes before and after. So that's the paired sample. If it's not exactly the same people that you're looking at twice, then you'll be using the independent samples. So for instance, when we're looking at complaint data, if we were to look at it across time, do you think it would be independent samples or paired samples? It's independent, exactly. It's not exactly the same people over time. Excellent. Okay, so when we're running, we'll talk about independent samples first. It's more difficult. Paired is much easier. So when we're running independent samples t-test, what you need, you'll need the two sets of data, obviously, that you want to compare. You'll need to know whether the variance is equal between the two groups. So like I showed you here, there are two different tests. There's one that assumes equal variance and there's one that assumes unequal. So you'll need to decide, are they equal or unequal? And the way you do that is with another test. It's called an F test. So I'll show you how to do that. You'll need a null hypothesis. And we haven't really talked about hypothesizing and what that entails, but basically what it is, it's an assumption that there's no difference. When you go into that test, you're assuming that there is no real significant difference. And that's called a null hypothesis. There's no difference. It's often represented with a 0. So what you're looking for is to set an alpha value. And what that is how confident you want to be in your conclusion. So we often set it at the 0.05 level. I know we talked about this when we were talking about the sample sizes. And I told you I'd explain what the 0.05 means later. Basically what 0.05 means is probably the most common alpha level. And what that means is that there's a 5% chance that you're wrong with your conclusion. So what happens is, and you'll see when you run a test, what we'll get is a p-value on the other side. So we'll decide as a group, okay, we want a 5% margin of error. We want to make sure that we're at least 5%, 95% confident that we won't make a mistake. We want to minimize our chance of mistake to 5% or less. So once we've set that parameter, we run the test, and then we look at what's called the p-value. And the p-value will determine whether we accept the null hypothesis or we reject it. So basically what I'm saying is, if it's above 5%, if our p-value is above 5, we keep the null hypothesis and we conclude there is no significant difference because my chance of being wrong is over 95%, and I don't want to be there. But if it's less than 5%, the p-value, then we can feel pretty safe in saying, you know what, I have a 98% confidence level or 99% confidence level that there is a significant difference, and I'm comfortable with being wrong if that's the case, because it would be such an extraordinary incident. So that's an overview of what that looks like. We'll look at it in numbers in just a moment. But what is important to know is that you set the alpha value ahead of time, and then you look at the p-value and compare the two. And that's what helps you. The p-value is what you get back from the statistical analysis. It'll give you the finding and then the confidence level of your findings. It's the p-value that helps you decide whether there is a significant difference or not. So usually when I'm looking at an analysis, I look at the p-value first, because if it's above my threshold, then I know that none of the rest of the numbers mean anything. There's no significant difference. If it's 5% or below, then I know there is a significant difference. So it's time to look at the numbers and see what it's telling me.
Well, I thought we were comfortable with 5%.
5%, so we want, I know it gets confusing because it's like 5% or 95% confidence interval. We want 5% or smaller for the p-value. And that means that we can be 95% or more confident that we're correct. We'll go over it a couple more times. But you'll want the probability to be a low number. And like I said, the most common p-value or alpha value is 0.05, and the next most common is 0.01. So that means there's only a 1% chance that you're incorrect. but that's completely discretionary. So this is another place where, so for instance, I was asking somebody about small sample sizes, and we're working with small sample sizes, what you do. And he basically said, if you're in a situation where you want to be able to run an analysis, you might want to just drop your p-value or your alpha value. He said anything above 50% is really, could be significant or is at least noteworthy. So this is set by the field of statistics, but you can play with that. I've seen 90% or 0.01 in terms of the p-value and alpha value. So it's discretionary. But if you're the kind of person who just like wants the rule, just stick with 0.05. You'll be good. So I have a flow chart here, if you're a flow chart type person, of what exactly to do, what the steps are to conduct the samples t-test, and we'll go through it. So step 1 is to run the f-test. And what you're checking for is in purple, that the p-value of the f-test is less than the alpha value. And if it is, then you take the path on the left. If it's not, take the path on the right. So basically, if it is, you run a t-test assuming unequal variances. If it's not, equal variances. And then you check to see, once you run that test, is the p-value for the two-tailed test less than the alpha value? If it is, you reject the null hypothesis. If it's not, you accept it. That all probably sounds like French, and that's okay, because we're about to go through all of it with you. But first, to put it in context, so the question that we're going to answer is there a difference in the number of children between the stat students at NYU and New York City employees? So I teach a class semi-similar to this to New York City employees. I pulled the number of children that they have from the last class that I taught, and what we'll do is do a side-by-side, and we'll see if there's a significant difference. So we'll go through this step by step, and we'll start with running the f-test. So come to this slide with me, and that's slide 23. And then if you open up this Google document, you'll see the new data that I added. And then just remember, you need to download it. So go to File, Download as a Microsoft Excel file.
How to get it?
It's in slide 23. So come to class 5, slide 23, and it's this link down in the bottom right-hand corner. So I'm going to run through really quickly what we're going to do, and then we'll do it. But what we'll do is come back up to the data analysis button in the data tab. Then we're going to choose the f-test, and that's in the list. You can see it's two options above the histogram. What we'll be choosing are the options that we select are variable 1 and variable 2. So those are the two things that you want to compare. You'll set the alpha level. You can see I set it for 0.05. And then you choose the output range. It's very simple. It's very similar to what we've done in the past.
Sorry, what's the step before this?
It's to just choose the f-test for 2 sample.
Okay.
I'm going to do it with you. So I'm just going over like what those steps are. Don't feel pressure to keep up. So then the output is going to look something like this. Now the one catch or the trick with the f-test is that you need to make sure that the F number is greater than the F critical. And so it's not here. And all that means is that you need to change what you selected as variable 1 and variable 2. I know that there's a statistically sound reason for why that happens and why you need to do it, but it's not worth going into. It's not even worth knowing, to be honest with you, in my opinion. More importantly is to make sure that if F is smaller than the F critical, that you need to flip it. So like here. So then I go back and I switch my fields for variable 1 and variable 2. So now I have B in variable 1 in column C, or sorry, A in variable 2. And then I check again. The new results, my F is smaller than my F critical, which is good. So the next step is to interpret the results. And what we're looking at, like I told you, is the p-value. That's this one here. And if it's smaller than 0.05, it means there's a significant difference. So for this that was run, there is a significant difference between the two categories. Make sense? Well, let's do it, and then I'll check again. Okay, so.
Sorry, can I interrupt you for a second?
Yes.
Very out of context question. With the new laptop, can you just remind me how I get the data analysis
Yes.
thing? Sorry, I just don't have my older one and I can't find it.
That's okay. So if you go to File, and then go to Options,
Okay. Just on add-ins.
Add-ins, and then down at the bottom, click Go, and check off Analysis Toolpath.
Ah, sorry, thank you.
I would do a VBA too, just in case.
What to add?
Which one do you add? It's the Analysis Tool Pack. So Add-ins, Go, Analysis Tool Pack. Analysis Tool Pack. The first option. Okay, so that's for the F test. And that determines, I apologize, I misspoke. What that determines is whether the variances are equal or unequal. So for us, since the P level is below our thresholds, yeah, it's smaller than 0.05, it means that the variances are unequal. So you move forward choosing the t-test for unequal variances. I can see the confused looks, and that's okay. I'm just acknowledging. I'm acknowledging where you're at.
French. I speak French.
And it didn't sound like that either, did it? What's a better language? It still sounded awful. All right, so our question is, are the number of children for the NYU class, you all, is that equal to, or is there a significant difference in the number of children for NYU as compared to the New York City employees? Just eyeballing it, what do you think? Any guesses? Yeah, that 5 in 4, 2 4s in particular. My gut would tell me, yeah, there's a difference. So we're about to find out.
Hi, sorry to interrupt. Do we need to have the same sample size? Because it seems like the sample sizes are different, right?
They are, and you don't necessarily need the same sample size.
Okay, got it.
It's a good question though.
Yeah.
Okay, so our F test. So let's go up to the data tab, and we'll go to data analysis. And we're going to check off or select the F test to sample for variance. And remember, this is the first step for independent t-tests. So if the samples are independent of each other, if it's not exactly the same people, this is the first step. We need to figure out if there are equal or unequal variances. So I'm going to click OK. The variable 1 range is just one of the sets of data, and we're using the raw data. So I'm just going to select all of the children at NYU for NYU students. For variable 2, I'll select all of the children, entries for New York City employees. I did not select the labels, so I won't check off my labels box. The alpha level is already set for me, which is perfect. And then I just want to select the output range. I'm going to stick it down here in A19, but you can put it wherever you'd like. And then once you have all of those filled in, you can hit OK. That's weird. Oh, I always do that.
What did you do?
When I select output range radio button, I always forget to click inside this, right? I did that last class too, before I select where I want the output to be. And so since I did that, it automatically filled in the A19 up here in the variable 1 range. So it overwrote. I do it repeatedly. Okay, so now we've got our F-test. Now, who remembers, what do we have to check for before we can read the results? Yeah, it has to do with actually the F and the F critical. Go back if you want. Let's go back to slide. Yeah, slide 27. So we want to make sure that F is greater than the result for F critical 1 tail.
It is.
And it is. Perfect. So we don't need to do another step. It absolutely is. So now it's time to read our p-value.
Could you say that in words?
Which part?
What would test? So right now we're checking if there's if the two groups are similar or not.
Oh, yes. What we're checking to see is if the variance is different between the two groups. If it doesn't matter if it is or it isn't, we can still run a t-test. It just changes which t-test we run. So we're checking for equal or unequal variances. We're assuming our null hypothesis is that they're equal. So we're going into this thinking it's equal. But if our p-value is 0.5 or less, 0.05 or less, then it turns out that they are unequal. But given our p-value here, what are anyone brave enough to guess? Is it equal or unequal variances?
Equal.
They're equal. That's right. Thank you. You saved the whole group in here. So they're equal variances. That whole exercise was just to figure out what t-test we can run. Does that make sense? Or do you want to redo that with something else?
How do you the variance, how do you know that they're equal then?
It's from the p-value. So again, it goes back to that idea of hypothesis testing. So we're going into the F-test assuming that the variances are equal. In most cases, they will be equal. The only chance that, the only way that we will safely say it's unequal is that we decided we want that p-value to be 0.05 or less. And it's greater than 0.05. It's 0.17. So that means that we can accept the null hypothesis. They are exactly the same. The variances are the same. And we can pretty confidently say that.
What's variance 1 times standard deviation?
Yeah, it's either, no, I think it's either squared or the square root. I forget which one.
I'm sorry, I can't download that file. I can't seem to manage to download this for some reason.
Oh, weird. Like from the internet, you mean?
From just clicking.
Did you went to file download?
Yeah.
And it won't do it for you.
It gives me the old one, the old version.
Weird. How about this? You could either just watch, because we'll do it again with a different data set, or if you want, you could just manually input these numbers. Do you want to run the F-test again on a different set of numbers, or do you want to move forward?
Just have a question.
Sure.
P, if it is greater than 0.05,
Mhm.
then we say it's equal.
If it's greater than that, we say it's equal. Yes.
We say it's equal.
Yes. If it's less, we say they're unequal.
Mean like equal to what? Or
The variances are equal to each other. So the variance for this group of numbers is equal to the variance of this group of numbers.
do we calculate that variance or how do we say
It's
that?
in here. So you can see that they're different.
Or you mean here, the variance of the year. Okay, I didn't see that.
So they are different. It's just that this p-value is telling us it's not significantly different.
Yeah, okay.
Any difference is just by chance.
If it's under the 0.05, why would you switch the data set?
Oh, it's not that. It's if the F is greater, or sorry, is less than the F critical one tail. Yeah, it's when you compare those two.
Why would you switch it? Or why would you? It just, yeah.
Rules. There are definitely people out there who will explain it if you want to journey into Stack Exchange. Yeah, that's kind of how I feel about it. Yeah. Maybe if we were studying it at the PhD level, that would be important, but not here. In terms of the flow chart, if you're having a hard time remembering, okay, well, what does the p-value mean, equal or unequal? I tried to make that really clear on the flow chart. So the question asks, is the p-value less than the alpha value? So is it less than whatever we set at the beginning? We set 0.05. So is it less than that? If it is, yes, then it tells you exactly what test. You don't have to worry about, is it equal, variance, unequal? Just follow the flow chart. Make your life a little easier. So for us, is it, yeah?
So logically, I'm thinking, I don't want to confuse others. If it's the alpha 0.05 is the margin of error, which means the 95% confidence level.
Yep.
So if I'm saying that it's the p-value has a lower margin of error,
You're right. You're good.
so it's
Go
the
ahead.
same. We should use it. We should use the.
It means that you can be safe in saying that there's a difference, that your null hypothesis is incorrect and there actually is a difference between the variances. And the reason is because you can be safe and confident in knowing that. We said we at least want a 95% confidence interval. If it was 0.01, we'd have a 99% confidence interval that there's a difference in the variance. Does that make sense? We're going to keep doing that. So every single test that we run, we set the alpha level and we look at the p-value. So we're going to keep coming back to this idea of the null hypothesis. So hopefully, if we say it in different ways and look at it in different situations, it'll click. So it's okay if it doesn't click just yet. We're like, again, we'll be revisiting.
The screen
Yeah.
is very difficult to follow.
The
It's very, it's
blurry.
The light.
Yeah, I was going to say, it was helpful with turning down the lights, right? Do you want to turn those off?
Because it,
Yeah.
Better?
yeah,
Okay.
because it whitewashes kind of.
All of it, yeah. Okay, good. Thank you for saying that.
Yeah.
I'm having a hard time reading it. I'm right next to it. Okay, so we checked, we said the p-value, is it less than the alpha value? And the answer was no. So we'll follow this path, which means that we need to run a 2-sample t-test assuming equal variances. So let's go back into our data set. We're going to go back to data analysis. And we're going to find that t-test assuming equal variances. And click OK. This looks exactly the same. Here, it doesn't matter which one's variable 1 and which one's variable 2. So just select. So variable 1, I'm going to choose the number of students, number of children for NYU students. Variable 2 for NYC. One additional thing that we need to add in here is the hypothesized mean difference. What that means is, what are we assuming the difference is? And the answer is 0. If you just want the rule of what do I put in there, always put 0. That's our null hypothesis. We're assuming there's no difference. I did not select my label, so I will not check off that box. My alpha level is already set for me. I'm going to keep it at 0.05. I'm going to select my output range, and I'm not going to make the mistake of not clicking in the box before I select where my output will go. And then I'll click OK. Does anybody want to see that again?
Yes.
Yeah, let's do it again. No worries. Okay, so we go up to the data analysis button. We select t-test to sample, assuming equal variances, and click OK. So it's already filled in for me, but I'll just go through. So variable 1 is just one of the columns of raw data. So I chose A, column A's data. For variable 2, it's what are we comparing it to? And that's the number of children for New York City employees. The hypothesized mean difference, you need something in there, it won't let you run it if you don't. And a 0 is what goes in there. And that means we're assuming there's no difference between the means this time of the two groups. I didn't select my labels, so I won't check that box off. Alpha level is already filled in. And then output, just select a place that you want your output to go. Okay, and then you click OK. Okay, so we get a lot of information here. Like I told you, once I run any sort of statistical analysis, my eyes immediately go to the p-value. Because if it is above my alpha value, it just means that there's no difference. So with our p-value, is it above our alpha value? Is it greater than our alpha value?
Yes.
Yeah, it is. Our alpha value is 0.05, and this is 0.18. So that means there's no difference between the means of those two groups. That means we were wrong. Even though the New York City employees have these great number of students here, there's no real difference between the average number of students for all of you and the average number of students for that last class I taught in New York City. Does that make sense? One thing I will say, and Simeo, that might have been what was sparking, you know, like some concern in your regard. It's okay that these sample sizes are not equal to each other, but they're very small. So one thing that might be throwing off this is how small the sample size was. If we increased it, we might see something different.
Okay, I see. But would it be ideal to have the same sample size?
I don't think it's my impression that it does not matter.
Okay.
I could be wrong. And I'm open to you telling me that, like if you find otherwise, but it's my impression that that doesn't matter.
Okay. And here from this test, we're generalizing our result to the population level, which is the NYU students and NYC employees, right? From this sample.
That's right.
Okay.
Yep.
Also, like column 1, you have like 9 data sets, and column B, you have like 14.
Yeah.
Does that make a difference?
Yeah, that's what Simeo was asking, and it does not. And that's my impression. That's from my recollection. I could be wrong, but I don't think it matters. I do think you wouldn't want 5 and then 110 and comparing the two. I would begin to think that that might cause some problems, but they're pretty similar in size. Any other questions?
My numbers are different.
Yes.
Yeah.
Do you,
It's one.
weird.
Mean is like
1.1111, right. Variable 2 is 1.2, 57,
The observation is like 9.
14.
Yeah, 9.
That's interesting, because yeah, you would think it would be, are your numbers here the same as here?
Yes.
I must have done something weird. Do you have 6 observations in 11?
No.
That's what it is. I didn't include all the data in running this. Is your p-value also above the alpha value though?
Yes.
0.1000. Yeah.
Okay. All right, good. Well, at least there's that. But yeah, you can see I didn't include all the data.
This Yeah,
Okay.
There's
Values,
p-value
right?
of 1 tail and p-value of 2 tail.
Yeah. So that's another, like, when we're studying statistics, that's important. What I would generally tell you is that look at the two tail.
2 tail.
What it means, and you can take it or leave it, what it means is that if you're looking at one tail, it means that there might be a difference on one end of the normal distribution. Whereas most of the time you might have a difference on either end. That makes sense. If there's no way that there could be a difference on either the positive end or the negative end, then you can do one tail. But normally there's a probability that it could skew either way.
So the tail is the
Yeah, it's thinking about the bell curve.
viscous.
Yes.
But if it's just one cell.
So I'm trying to think of an example of when that might be the case.
I mean,
So what I will say is that when it comes to the number of children, it's possible that the number of children from New York City employees could be, the average could be higher, and it also could be lower. It could be either. That's the two tail versus a situation where it could only be higher or it could only be lower.
for example,
I'm trying to think of a good example. I can't think of
situation
one.
of employment, non-employment, for example. You know, there's a probability that it's just one cell.
Yeah.
It's either employed or not.
Yeah, that could be it. But most of the time it's two-tailed. So you're safe going with two-tail. Okay, so we're going to go back to that. Like I said, we'll revisit this. This is just our first touch at that. But to review, we ran the F test. Then we go back to the data ribbon, since we found out that, well, in the one that I ran, there was unequal variances. For us, there was equal variances. So you choose the correct test, you select the variables, you enter the null hypothesis, you read the responses. This next slide goes over like how you report. So if you're running or if you're reporting to a statistically savvy audience, what you have to report are the t-value, the degrees of freedom, that's the DF, and the p-value. If the difference is significant, you should also provide the contrasting means for each of the groups and their standard deviation, which is the square root of the variance. So the variance is squared, standard deviation. So what that looks like is this. And whenever I'm reporting to a statistical audience, I usually take this and I make it like ad libs. I just pull out the numbers that were there and I put in my own numbers. So it says a t-test was conducted to determine if the mean number of children for NYU students is significantly different from the mean number of children for NYC employees. The results indicate that t-value of negative 3.47. So you can see where I pulled that up here. There it is, it's t-stat. And the degrees of freedom are 20. You can see that there. With a p-value of 0.002. Which is significant at the 0.5 level. So you have to tell them what your alpha level was. The mean number of children for NYU students, and so that mean is the 0.25 with a standard deviation. Where do I see that? 0.71. I think I had to calculate that on my own. Oh no, it's the square root of the variance. Yep, so I did the square root of that. And that's significantly different from the mean number of children for New York City employees. And then I report the mean and the square root. That's a huge mouthful. It's really complicated. If you're writing for anybody else, you can just say this. There's statistically significant difference in the number of children for NYU students as compared to NYC. So if you're writing a report, go for this. If you just want to draw a conclusion and speak to lay people, that's perfectly fine. Okay, any questions about that?
I wanted to know the F and the F significant. But you said that's PhD level, is it?
The difference between the F and F significant?
I mean, what are we
Yeah,
looking for?
You're just looking for F to be greater than the F sig. Yeah. I go really deep into the whole, really for all of you. And then I'm like, okay, is this worth sharing? Is this not? That was not, I didn't even get to the end to understand it. I'm like, this is too much. It's just too much. Okay, so when it comes to the paired sample t-test, so that was independent. When it comes to paired, this is like the pre-test, post-test, exactly the same people before and after. What you need is very similar. Like I said, it's a little bit easier. So you need two sets of data. You need the null hypothesis, that's exactly the same. And then you need the desired alpha value. You don't need to do the F-test anymore. You would assume that the variance is the same. So you run a totally different test. And again, you want the probability to be a low number, and usually we use 0.05, if not 0.01. Here's what the flow chart looks like. Much easier, right? So basically you run the t-test and you read the results, and that's it. We don't have a good example of that. I haven't tested you or found out how many kids you had before and then after, and I assume everybody stayed the same. But what it would look like, or a way that we could explore something like that, is that if we were to look at the number of children in the diploma program between 2015 and 2020, like, is there a difference in the 5-year period? So I might take a class from 2015 and compare it to you all. And if I had that data, this is what that would look like. We'd go to the data tab, we'd run data analysis. This time we'd choose the t-test paired to sample for means. So we were looking for paired in there. Setting it up is exactly the same. You select the variables, you enter the hypothesized mean difference, which is 0. You select the alpha level or keep the alpha level the same, and you select the output range. And then when it comes to your results, you read it very similarly too. So the P level here, for the difference between the kids, is there a significant difference between 2015 students and 2020 students?
Probably.
Why do you say that?
There is, because it's less than
Yeah, less than
0.05.
P is
I
greater
think
than
0.06.
So 0.06,
Oh,
so that's higher than.
Yeah, 0.06 is higher.
Good.
There's no difference.
There you go. Perfect. There's no significant difference. Very good. So again,
Question on the sample.
Yeah.
See, if you're looking at students in 2015 and 2020, those are a different set of students.
that's true. I would have to, it's a really good point. I did not set that up well. If I had asked you how many kids you had in 2015 and how many you have now.
Right, so that's how the exact same people have to be surveyed.
Yes, thank you for that correction. I should fix that. Again, when it comes to reporting,
Oh, you don't have that here.
okay, no problem.
Okay.
Yeah, no problem. Okay, so again, the reporting is very similar. You would just say there is a significant difference, there isn't. For your homework, I would encourage you to do this more formal method just to practice it. Again, you can copy this and paste it and plug in the correct numbers, but I would say it's worth the practice. Practice with me, even if you never do it again.
How do you copy from a slide?
You should be able to read it, maybe not edit it. So you should be able to highlight still and copy. If you can't, you're not able to, I can send you the, yeah.
So which slide did you correct? The sample? The slide.
Which one do I need to correct?
Just what Farida raised just now.
I'm sorry, say that again. Oh, which,
She raised,
yeah, it was 39. I need a better example here. Yeah. That yellow to remind me. Okay. So take a moment. 1, 2, 1, 2. Oh, good. You pair up perfectly. So pair up with somebody next to you. Pick who's A and who's B. And then partner A, explain when do you conduct an independent samples test and go over the steps. And then partner B will be the paired sample test and what are the steps. So go ahead and talk about that.
The same person. The same the person is the same, but the number independent just because how many you have
Less or more.
Is less.
No.
If it is less than,
Yeah.
then okay, that's the only difference. Greater than, the rest of it has the same thing.
Okay. Yeah. And then there you run your.
You conduct an example test.
where it was the same person but on a different time.
That the variance is the same.
Yes, steps of for, or it's like more. You want to be.
So you do the compared test when you're studying the same steps for that.
When you go for a
Yes, so you p-value is the test. Yeah, so the p-value is less than.
Compared samples. It's when you have
Yeah, because if it's less than, that means that it's not really. It's very.
I would love someone to say, but just to make sure I've got it 100%.
Sure. For both of them?
Yeah.
Does somebody want to share for the independent samples test? When do you conduct it?
The two samples are different.
Yep, when they're different people. And then the steps. I'm going to go back to the flow chart if that's helpful. So what's the first test that you have to run? The F test, exactly. And we're testing for unequal variances, whether they're equal or not. If it turns out that the p-value is smaller than your alpha value, which t-test do you run? Unequal variances, exactly. And then once again, you're looking at the p-value, right? And if the p-value is less than your alpha value for your t-test, what's the conclusion? There's a significant difference. Exactly. You reject the null hypothesis. Perfect. Very good. And then when it comes to the paired sample t-test, when do you run that one?
Well, when you have two variances that are equal.
Yeah, the two groups are equal. And in fact, it's exactly the same people, right? Just at two different points in time. Good. And then you just run the t-test, the paired t-test. And then what happens if the p-value is greater than your alpha value? What does that mean? There's no significant difference. Excellent. By the end of today, you will have that so concrete in your head because I can hear it already clicking. That's great. Okay, so the next phase, I did the harder part first so we can do a little bit easier. It's only uphill or downhill, I guess it would be from here. So the next question, so we just asked, how do I compare groups of people? And that's through the F test. Now I'm asking, how can I tell if there's a relationship between indicators, if one influences the other? And the way that we do that is through correlation. So correlation, it describes the degree of a relationship between two continuous variables. So that's another distinction that we'll get into, what that means when it's continuous versus non-continuous. One thing to note, and which makes it a little special, is that it can be both descriptive and inferential. I'm trying to remember when we ran the descriptive statistics, did it have correlation in there? I feel like it might have in that summary. I know it had skewness, maybe it didn't. But know that it can be descriptive and it can also be inferential. So my point in saying that is you might see a correlation run for population data because they're running a descriptive statistic. Again, if it's a sample, that's the only time that it's inferential. So yeah, like I said, it can be used population and census data. And the relationship, there are two different types of relationships that it can find. It can find a positive or proportional, which means that when one of the values goes up, the other one goes up. So an example of that is height and weight. Oftentimes, if height goes up, weight goes up. It's not always the case, but that's usually the case. And then the other relationship would be negative. And that doesn't necessarily mean when one goes down, the other goes down. That's actually still a positive relationship. Negative is the means they go in opposite directions. So when one goes up, the other goes down and vice versa. So an example of that is class absence and overall grade. So the more you're absent, likely that the lower your grade drops. Again, not always the case, but usually.
So what is continuous variable?
Yeah, we'll get into
Oh,
that.
yeah.
I'll make that distinction.
Okay.
I almost don't want to make your brains explode today, but we'll get there next class. Yeah, I know. That's why I know I'm on the brink, which is exactly why I brought the treats. So you can pass those around, Susie. This is always the moment where people are like, I need some brain food. So I'll get there, Nita. I'll get there.
Because even the height, I think that example I was thinking it's only up to the age of 18 or something, after which your height doesn't change.
That's a good point. And actually, it can become negative, couldn't it? I'm trying to think of the relationship. Like, you might also, I guess you might lose height and weight as you get older. So I assume it becomes positive. But you're right. We'd be talking about 0 to 18 for the best positive correlation. So as evaluators, it's useful when we want to determine how two factors might influence each other. So an example might be, how is gender related to success in schools? So if we have a column with gender and we have a column with grades, we could look at the correlation between the two to see if there's any one impacts the other. Another one is borough in which a person lives related to pet ownership. So both of these examples actually are using categorical, right? Gender and borough are categorical, but this is more so to give you an idea of what I mean when I'm talking about correlation. How do these two things play with each other and affect each other? So what we're looking for is the correlation coefficient, and that's a single number. It provides a measure of both direction and the strength of the correlation. So it ranges between -1 and 1. If it's negative, like if it's below 0, then obviously that's a negative correlation. So that means one goes up, the other goes down. And if it's above 0, up to 1, that means it's a positive correlation. One goes up, the other goes up, one goes down, the other goes down. And, right, that's what I just said. And then the closer they are to either -1 or +1, the stronger the correlation is. So if you have a -1 or +1, it means they are very, very, very strongly correlated. If you're at 0, there's no real relationship between the two.
Is this called the beta value in terms of Greek letters? Beta.
It might be, I'm not sure. I'll look. So here's examples of what correlation might look like. A 0 is just random. They're just plots, dots on a plot. A -3, you can start to see the negative relationship coming out. This is what now, so we go from -3 to -0.7. So they're getting closer to looking like a line. And then here's almost a perfect negative correlation. You can see that line playing out. And then similarly, if we were to look at 0.5, you can almost see the line. You could draw the trend line in there. And then 0.9, you can almost perfectly see that line. So just some examples of what that might look like. And then for reference, the x-axis is one of the variables and the y-axis is the other. That's how these are plotted out. So that's how we would calculate correlation by hand. Thankfully, we don't have to because it's so much easier in Excel. It is literally just the formula CORREL, C-O-R-R-E-L. And then as you can see, you highlight the two groups, just like we did for the F-test, just like we did for the T-test. And then the answer we read as such. So that's pretty close to 1, which means it has a positive correlation. So what becomes tricky, I guess, about a correlation is that it's hard to determine what actually means what. So I could tell you that the closer you get to 1 or -1, the stronger the correlation is. I could tell you that a 0 is no relationship, but everything else in between becomes really arbitrary. So I did find online a guide. Oh, where is it? Here it is. I found online what one study used as their guideline, and I really like this because I think it makes it concrete. Again, this is just one group's, how they decide what's significant and what's not. This too is arbitrary, but I would say let's use this as our guide. I think it makes sense. So here they're saying if it's 0.8 to 1, it's a strong correlation, moderate, weak, and then no. And similarly, it does the same thing on the negative end. So when we find our correlation coefficient, we'll go back to this and look up whether it's a strong relationship, it's no relationship, or whatnot. So when we're running correlation, what you need are 2 sets of continuous data. So you need the raw data for the 2 groups, and then you need the Excel formula. It's as simple as that. Let us do that. Oh, let me just talk about reporting really quickly, and then we'll do it. To report the results, you need to share the degrees of freedom and the p-value. If the significance is different, you should also provide the contrasting means for each of the groups and their standard deviation, which is the square root of the variance. So an example of that, a test for correlation was conducted to determine if the number of children is significantly correlated to the number of years living in the city. There was a strong positive correlation between the 2 variables, and then you just report what that looks like. That's an example. And actually, I think I might have copied and pasted from T-test that all of that is not necessary. What you need to share is, in the end, the correlation coefficient, which is described by the R equals, and then share what that is. I need to edit that slide. When you're reporting to anybody else, you could just say there's a strong positive correlation between the 2. One thing to note, and if you've heard of correlation, you've probably heard this too. Correlation is not causation, right? One does not necessarily cause the other. So for instance, to be taller does not make you heavier. It's not a cause and effect. It's just that they're related, they're linked. And the reason for that is that there can be confounding variables. And what I mean by that, here's a really great example of a spurious correlation, like an incorrect correlation, that has this God, what's the word I'm looking for? The confounding variable in there. So here, and these are actual numbers, the divorce rate in Maine, and how it's correlated with per capita consumption of margarine. So when the margarine use goes up, the divorce rate goes up. So what do you think? And look at the correlation. It's almost perfect, which almost could lead you to believe that, like, please don't use margarine, because especially if you're in Maine, because you will get divorced. But that's just not sound. That sounds ridiculous, right? What do you think could be?
Well, you're not, yeah, you're not buying, you're now not buying for your family, you're buying for yourself, maybe.
Yeah.
So you're doubling.
Mhm.
That's the only thing I can think of.
Basically, what it's saying is that correlation does not show causation. No, it does not. However, we talked about at the beginning of, I think it was session 1, we talked about how you need to pair the statistical test with a really good design, evaluation design. Between those two, you can talk about causation. So if we had this really strong correlation and we designed the study with the intention of seeing if margarine is related to divorce rate, and we sampled perfectly and we set it all up well, and we got that correlation coefficient, then we could say that confidently. But these are just two stats that people randomly smushed together and did a correlation of, and oh my goodness, look at that. There's a positive correlation. You can't do that. You need the good design complemented with it. Does that make sense? And that's true with any test. A t-test is not going to say anything if you don't have a good design behind it. Okay.
I can also share what a beta is. It is related, however, it's only related to the stock market. So the beta is a measure of a stock's volatility in relation to the market. So if a stock moves less than the market, the stock's beta is less than 1. And if high beta stocks are supposed to be riskier, but provide a potential for higher returns.
Interesting.
And low beta stocks pose less risk, but also lower returns.
Okay.
So they also talk about -1 and +1 in terms of what the index is doing, what the
Interesting.
beta value of the stock is.
Cool. Yeah, I can see how those could be conflated pretty easily. Yeah, thank you.
Could you explain the confounding variable?
Yeah, what does that mean?
Yeah. For example.
So a confounding variable here could be, well, can anybody think of what a confounding variable might be? Like, what is a third factor that isn't necessarily considered that might impact your use of margarine and your divorce rate? So one thing I can think of would be maybe income, right? If you have lower income, and I actually don't know what the divorce rates are for low income, if they're related at all, but maybe low income causes more stress, more divorce, and also might cause you to use margarine. So it's not actually that the one is impacting the other, one is not causing the other. It's really income that's the confounding variable in there. It's just, what it means is it's confusing the results. So if we were designing this study, we would definitely need to take into consideration income.
How's calculating a correlation helpful?
It can tell you, point towards causation. All of these things can point towards one thing causing another. Here in particular, it's looking at two variables within a data set and pointing towards causation. When it comes to the t-test, it's more about, is the outside influence that I put in causing a difference? There's a little bit of a distinction.
What does degree of freedom mean?
So that, I think, is 1 minus the number of variables in the study. And that, I forget what it means, but that's how it's calculated. I do remember my stats teacher telling me this. I just don't remember what she said.
Look it up.
Yeah. It's not too complicated. It's worth looking up. You won't regret it. Any other questions?
So here, when we calculate the correlation,
Yep.
do we need to do a hypothesis testing for statistical significance?
For the correlation?
Yeah.
Yeah. No, you don't necessarily have to have a hypothesis. I guess the hypothesis would be that there is no correlation, that you'll get a 0 or around,
Yeah.
but there's no rejecting a null hypothesis.
Okay, so it's not like necessary to do another test on top of
No.
this.
It's
Okay.
just running correlation.
Okay, got it. But then can we generalize this result to
Yeah.
from the sample to population? Okay.
Yeah. When you're running it on a sample, you can generalize it as long as it's a properly drawn sample.
Okay, good.
Any other questions? Okay. So that's us for today. Oh, I have a little cartoon. Our relationship entered its decline at this point. The person said that's when he started graphing everything. The person said that's a coincidence. Okay, so when we're talking about this study, this study of well-being in New York City, if you're in your slides, you can go to slide 64, and that picture is a link. So let's open it up. And my question for you is, let's go to page 59. And how is a correlation analysis used in this study? They use a correlation analysis. I want to give you some real world practice or exposure, I guess. It's in that data validation section.
Page 64.
59.
So it's basically looking at how those two variables are correlated, like economic security and housing.
Yep.
Or health and education, how they're correlated.
Yep.
Fascinating.
It is. My impression of what they did is that they took, and actually I think it keeps going. Oh no, it doesn't. I remember reading somewhere else that they used correlation to figure out which indicators were in and which ones were out. So if there was not a strong correlation between the two, so if there was, let's say we were testing a particular health indicator and it was not strongly correlating with any of the other categories, that helped them to decide to discard that one. So what they were looking for is overall in the whole index for all of them to be pretty strongly correlated with each other, because that gave them the confidence to say that this is how we can measure well-being in New York City. Does that make sense? So just a real world example for you. Okay. So let's do a practice. I think we can do it together. Well, how are you feeling? Do you want to do another round of both of the different tests together? Or are you feeling confident enough to do it on, yeah, okay. We'll do it together. Got you. Okay, so because we don't have our own raw data for this index, so one of the challenges is we don't have the data that they used. We just kind of know what categories they wanted. We can't easily conduct our own in or out. But what we can do is explore the relationship into the types of complaints. So a question that I have that we can answer with a correlation is there a correlation between the number of residential noise complaints and the number of business complaints? So first, do you think that there is a correlation? What would your gut say?
Yeah.
Probably, right? And would it be positively or negatively correlated?
I think negative.
Why do you think negative?
Well, I mean, basically because, you know, businesses tend to be very loud, you know, versus, you know, the demand of just private, private, you know, areas and just different needs and different expectations.
Good. Okay. And then tell me, Susie, why did you say positive? How about this? Let's go back. 168.
Maybe, I don't know, I don't have a good thing. I don't know. I was thinking, I don't know, if people live near their businesses, in terms of population density, if there's then more people, the noise will be high.
Yeah. Good. If it's noisy for whatever reason. So let's remember that positive, it means that they're proportional. One goes up, the other goes up, or when one goes down, the other goes down. And then similarly, negative is inverse. Like an example I would give, or a thought that I would have, is if people are going to complain, they're going to complain about everything, right? Like they're just unhappy, they're unhappy. So in that regard, I would say a positive proportion. It's possible though, and I think what you're getting at is it could be negative, because if people are in a residential area, there might not be businesses around that they're complaining about, and vice versa. If they're more industrial, there might be less residential noise complaints.
The more it's business, the more less residential.
Yeah. Yeah, and that's a really good point too. So it could be either, but would we assume it's correlated? And I think most of us said yes. It will probably be correlated. We just aren't sure how. Okay, so that was my first question. Is there a correlation between the number of residential noise complaints and the number of business complaints? I know I was going to ask you a follow-up question for that, but I can't remember what it was, so we'll keep going. Okay, so let us download the residential and the business noise complaints. If you already have them on your computer, you can just pull them up. They haven't changed at all. But if you don't have it on your computer, let's download. Okay. So when we're running a correlation, just going to move this up here. When we're running a correlation, we need to use the raw data. What we're going to be comparing are across the different neighborhoods. So let's move into the pivot tab. The other thing that's important is to make sure that we're comparing the same, like apples to apples. So what we'll do here is just compare counts of complaints. We're not going to normalize it. We're just going to compare counts. So for correlation, you can choose either data set. I'm in business complaints, but again, it really doesn't matter. Just choose an empty cell. And who remembers what the correlation formula is?
Or
Yep, CORREL. And it'll prompt you for what we're running. So the first array is just the first set of complaints. Make sure you highlight everything starting in row 2. And it'll go down to row 60.
so we didn't count of businesses, no.
Just count of complaints. Yeah. And then type a comma. And that'll move you into the second part of the formula, which is to select array 2. So then I'm going to go into my other data set. I'm going to find my count of complaints. And I'll highlight all of those as well.
Comma array 2, did you say?
Yep. If you type comma, it'll take you to array 2. Like it'll ask you for your second array of data. So in the end, my formula looks a little funky because I'm going between data sets. But for me, I have B2 to B60. And then I move into this other residential noise complaints pivot table that tells me the name of the file and then the name of the tab. And then I'm again looking at B2 to B60. And once you've got all of that, you can close your parentheses and hit enter.
They're not correlated.
They don't seem to be.
Oh, I didn't, there's a problem with the formula.
Let's try again.
Is this your, after, because we're using it in the, this is after you remove the outliers?
I'm trying to figure that out.
That should like give you a result. I don't know why it's saying anything.
Yeah.
Nita, how's it going? Did it work the second
I'm
time?
just about to hit enter.
This is like a session 0 question. The data that we're looking at, the residential noise complaints are complaints received from residences, and the other one is complaints received from businesses.
It's 4. So the residential noise complaints are complaints made.
About a business and about a resident.
Exactly. Yeah.
Say that again?
It's a complaint made about a residence or about a business. The residential noise complaints also are if there's anything happening outside of somebody's residence, so on the street, sidewalk.
I'm just getting one line, 10.8.19. something. Right. It's too dark also for me to figure it out. I could just go this way. I just started
It
again.
seems to have lost. Wait, here it is though.
This one? It's just this.
That's the answer.
Okay. Yeah.
You got
I
it.
was thinking, there would be like
Oh, the
other
big
things
feedback.
here.
Yeah.
yes.
No, with correlation, it's nice and simple.
I got a 1. I don't understand why.
You got a 1.
Perfect.
Yeah.
So,
Yeah, I mean,
So I
too
learned
many
it.
episodes.
Yeah,
of
exactly.
Friends. That's what happens. My computer's already.
You did yourself like compare this to itself.
I've been using it
As
for
opposed
a
to
while,
right?
right?
So you're in
Oh,
business.
from like 4 years. So this
You should get the difference.
And see, I've been studying
Okay.
it. This was like, it's becoming after,
Okay, so if we were to go back, do I have my grid here? Yeah, I do. So you can see me taking you through the steps here. That's on slide 71 that we just did. And then here's the table again for comparison. So we fall into, what was it, 0.03. So that's definitely no correlation. It's not even close.
What about 0.1 minus 0.1?
Is that what you got? Minus 0.1?
Yeah.
0.1?
Yeah, minus 0.1.
How did that happen? But it would still be no correlation, so that's good.
Okay.
So I don't know, Sam, are you looking at your data after removing the outliers and such from previous assignments?
No, these are new ones.
No,
We can look at it.
that's the only thing.
Yeah.
Okay, so most of us got there, but you still got the no correlation, so that's good. We can look at detail to see what happened. So a test for correlation was conducted to determine the number of residential noise complaints is significantly correlated to the number of business complaints. There was an insignificant negative correlation between the two. Oh, so that's interesting. I got even something different the last time I ran this. But it's still insignificant, which means there's little to no relationship between residential complaints and business complaints. That's worth knowing. If we were creating an index, we would probably wind up throwing out either business complaints or residential complaints from the whole well-being study. But we'd want to run a correlation with both of those and other things as well to find out which one's the weaker link. And then we'd probably wind up throwing out. I'd assume it's business complaints, but I mean, maybe residential complaints don't have an effect either. I don't know. Okay, so I want to give you a chance to practice correlation on your own before we go back to revisiting t-test. So back, I think it was 2 classes ago, I asked you to make the decision which ratio to use if we thought it would make more sense to talk about the count of complaints per person or the count of complaints per business. And we decided count of complaints for business probably made more sense. But what we can do now is run a correlation and see. So what I want you to do is calculate. So you're going to open up the 2015 311 business complaints. And I want you to calculate the correlation between the count of complaints and the count of businesses to see if there is actually a relationship and what that is. And then I want you to look at the count of complaints and the count of people, like the population count, and see if there's a correlation. See if either of them are positively or negatively correlated.
So do you want us to divide the complaints per person or not?
No, you'll do the raw. So let me go to my business. So what I want you to do is do a correlation of the count of complaints and the count of businesses. So those will be your 2 variables. And then the other one I want you to run is count of complaints and the population, just to see if either of them are positively or negatively correlated. And again, you can do this as partners too. So if you want to do it with somebody, that's fine.
You're just typing. Here's notes. Yeah. You gotta learn to do this. You gotta learn to equal.
The third one is complaint and population, right? The third one?
complaint and population. That's really satisfying.
That works too. Yeah, so C is gonna be population, so if you wanna compare and see, so what this one is, you're finding correlation between the first array of data, which is counts and names, and then the second array is gonna be population. So you want to select your second array. Or if you wanna also compare complaints to population, also complaints to businesses. So right now, correlation.
And then comes up with like,
Yeah. Just hit enter, yeah. Yeah, and then 9 you want to do this. Yes, complaints, right? Complaints to businesses.
Basically doing the same what she's done.
No, it's this one right here, so we're just comparing the data sets in the spreadsheet, so.
0 points.
Yeah.
What'd you get?
The complaints of the businesses seem to be more correlated than complaints of population.
Mm.
Me too.
Same.
7, which is moderate complaints.
One tricky thing about correlations, it's kind of like standard deviation. You can't really compare across. But what we can say is that the complaints in businesses are moderately correlated, right? Whereas the complaints in population has no correlation. So there, at least we can say, yeah, we made the right choice, which is very satisfying. Our intuition was correct. Yeah. Yeah.
This basically means that the more businesses there are in a particular neighborhood, the more complaints that
Exactly. And it doesn't necessarily have to do with how many people there are.
Right, so it's just my number of businesses.
Yep.
If we look at this table. No correlation.
That makes me wonder about the correlation between the number of people and residential noise complaints. I know. I kind of want to. I guess it wouldn't be that hard. I'm gonna do it right now. I have it right here.
Yeah, I think so. Not so much.
you get 0.22,
Interesting.
not so correlated.
No. Oops. Where's my grid? What is it, 0.22? No correlation. Interesting.
Because like businesses are more noisy than humans.
Yeah. Huh.
Complaints.
So there's something else besides density of people that's causing people to complain. Okay, so did everybody get for the businesses data the same correlation? So for complaints and population, we got 0.13, which if we go back to this grid, we can see 0.1 is no correlation. It's in that range. Okay, so that's interesting. And then in terms of complaints and businesses, we got 0.71. And so again,
I go 7.3 again.
7.3. It's
Yeah.
close.
Yeah.
Either way, you get the right answer or the same answer, which is there's a moderate level of correlation, which to me, my conclusion is that we guessed right, that there's a stronger relationship between the number of businesses and complaints as opposed to people and complaints. And is it positively correlated or negatively? Positively, which means what?
They move in the same direction.
Yes, when there are more businesses, there are more complaints. Great. And then for funsies, I looked at residential noise complaints and the number of people to see if that was related. And there's no correlation there, which is interesting. Okay, so there's that. And again, like we can't talk about causation because we don't have a properly set up study, but it's interesting to see that there's no real relationship there, and we can say that. Okay, great. So we've got the correlation small group practice and we interpreted it. So let's go back to t-tests, the more complicated of the two. So we'll go back to this idea that we were recruited by CIDI to update the report. And so not only did we want to add indicators, which we looked at different indicators, but they also wanted us to look at any changes in the ratings. So to see if this was 5 years ago, if there's been any change in for us, it'll be the number of complaints back then and then now. So the question more concretely is there a difference in residential noise complaints between 2015 and 2018? So my first question, well, actually, before we even do that, let's download the 2018 data, which I don't think we've looked at yet. So go ahead and download that.
I looked at dates for my last week's.
What happened? That's weird.
Residential business.
The residential 2018?
Business complaint. Yes, there it is.
Did I stop sharing?
Business complaints. It says, this one?
Yeah, that's the presentation. You'll go on the Google Doc. And probably doesn't look for that down. Okay.
This is one.
Oh yeah, mine failed too.
I thought you said it.
Okay. She said, oh, okay.
There we go. It's 2015. Okay. Just getting my screen set up. So I've got 2015 on the left, 2018 on the right. So 3 years difference. So the first decision that we have to make is which t-test are we doing? Are we doing independent samples or are we doing paired? Okay. Because it's 2 different years. And that's a good thought. Who said independent? I'm leaning towards independent. Tell me why you think that.
Those might be different people who are making the complaints.
Yeah. Yeah, it's not necessarily exactly the same people. So if it was paired, the intervention would be more like, is what we did making a difference for you versus for the whole neighborhood, and it's different people inside. So I agree, I think it would be independent. So then if we're running independent, what's the very first step to running an independent t-test? We have to run the f-test, exactly. Good, so I'm going to work inside my 2015 data. It does not matter which one you work within. So we're going to go up to the data, oh, this thing, move that down there. We're going to go up to the data ribbon and we'll click on data analysis. You'll want to find your F test for 2 sample variance and then click OK. Now, one thing to be careful of is it saves your entries for the last time you ran it. So you can see here, this was for the NYU number of students, and it's very small. And it's actually in the wrong column as well. So I'm just going to delete what was there. And we're comparing the number of complaints from 2015 to 2019. So for variable 1, I'm going to look at 2015. I'm just going to highlight all of the complaints. And then for variable 2, I'll delete what was there. And I'm going to go into the 2018 data. And I'm going to highlight all of the complaints here. Make sure you don't include the grand total. If you selected labels, make sure you check the box. Our alpha level is set for us already. I think that's fine. And then I'm going to change my output range as well. I'm just going to put it over here. There. Does anybody want me to talk through what I did in here again? Or are we pretty good with that? Good? Okay, so I'm going to hit OK. Oops.
18, so 15. We are doing 15 and 18.
15 and 18. Let's give them a chance to catch up.
Residential, yes.
Here. Here. So the first thing that we want to check for in our results before we even look at the p-value is that F and the F critical. And we want to make sure that the F is greater than the F critical. Is it? Good. So we're going to have to rerun it. And all that means is we rerun it and we change the variable 1 and variable 2. So this time my variable 1 is going to be 2018 and variable 2 will be 2015. So what I'm seeing that my F is a number that's smaller than my F's critical. Yeah, in order to decide if the variances are equal or not, you need the F to be greater than the F critical. It's just like this small, minute thing to remember. So I'm going to go back into my F test. And I just need to change. So variable 1, I highlighted 2015 data. Variable 2 was my 2018. And I'm going to switch them. Exactly.
Yeah.
So if F is greater than F critical, then what happens?
Yeah.
What does it mean in words?
It just means you're going to get the wrong answer.
So what does it mean in words?
That's one,
That is just,
That is
the answer will be wrong.
You have to rearrange it or just do the opposite.
Yeah.
Like they say, which makes sense. It seems less.
So this time I have 2018 as my variable 1, 2015 is variable 2. And I'm changing my output range to just make a chart below the original one. And then I'll click OK. So now my F is definitely larger than my F critical. That's good. That means I can read the p-value and it'll be correct. And my p-value, this is something interesting. It's not an error. This is a throwback to, for me, it's a throwback to the really old calculators. It's the exponential. So it's 1 to the negative 13. What that means is it's a really, really, really small number. So it's basically what it means is you take 1, and you know how the decimal point could go like this. Oops.
1 and 13 0?
Yeah. So what it's saying though is this is 1, the value 1. When it's to the exponent of negative 13, it means you take that decimal point and you move it to the left 13 times. So that's negative 13. If it was 1 to a positive 13, you would move it 13 decimal places to the right. So you'd make it a larger number. So basically what this is saying is that it's a really, really, really tiny number. It's 0.00000 13 times and then a 1. Yeah, or 12 times and then a 1.
But isn't it supposed to be a minus then?
It is. So you can see the E negative 13. That's a negative there.
Okay.
So basically it's saying take this decimal point and move it left 13 times. So with that, is this a number that is less than our alpha value?
Yes.
Yeah, like resoundingly, yes, absolutely 100% it is less. So what does that mean for our F test? What does it mean for our variance?
They run independent.
We want to run independent for sure, but does it mean we have equal variance or unequal variance?
Unequal.
It means unequal, exactly. Good. So let's go back to data analysis and we'll find the t-test assuming unequal variances. And we'll click OK. And then this time, whatever you choose for the variable doesn't matter. You can do the same thing you did last time. We could do 2018 for variable 1, but you don't have to. I'll just do it again for the sake of repetition. So variable 1 is one of the rows of the counts of complaints. Again, don't forget to not include the grand total. And then variable 2 will be my other count of complaints.
You need to include the grand totals?
Don't
No,
include.
don't include.
Sorry, yes, do not. The hypothesized mean difference, what goes here?
0.
A 0, good. It means that we assume that there's no difference. I didn't include my labels. I'm going to keep the alpha value the same. And I'm going to put my output, I'm just going to make another chart below this. Dang, I did it again. Ah. That's count a complete. My output range will be here. Does anybody need to see that again or understand what, do you want me to walk you through what I put in, or is that good? Good. Okay, cool. So we'll hit enter. And here comes the magic, which is, how do I interpret this? So we'll look at the p-value. Do we want to look at 1 tail or 2?
2.
Let's look at 2. Yep. And we've got the E again. So yeah, it's negative 13. So that means it's a really, really, really small number.
Could you explain that again?
Yeah.
This even,
What this is saying is you take the 3.23 and you take that decimal point and move it to the left 13 times. So imagine what that number would look like. It's 0.000000323, blah, 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 blah. So in that regard, is this number greater than or less than our p-value? It's less than, which means, is there a significant difference between the means of these two groups?
Yes.
There is. Good. So if there was any sort of intervention that took place between 2015 and 2018, it had a difference. There is a significant difference between the means.
But we don't know if the intervention resulted in a positive difference or negative.
That is the most frustrating part about these tests. And there's always somebody who's like, wait, but that's not really that helpful. It's helpful, but not terribly helpful.
We still need to go back and figure out what changed or how it changed.
Yeah. What I can say though, is I can look at the means and I do see how they decreased overall. So what it's saying is that, yes, there's a difference between the means and the number of complaints went down for variable 2. Now, unfortunately, my variable 2 was 2015, which means that technically the number of complaints went up over time. And so that's when you scratch your head and you're like, okay, well, if we did an intervention for 3 years, why are they going up? And there could be answers, right? Like let's play this out. What could be a reason that the noise complaints will go up, even though you intervened, even though you were trying to help improve the quality of life for New Yorkers? Population increase, exactly. We might have made them more aware of how to report noise complaints. So that'll go up. So there are many things that could impact that. Mm-hmm. Exactly. So, but overall, that's the conclusion, and that's how you read it. Make sense? We've gone a long way from Britney Spears' face to where we are now. All right, I think I have an example. I wish I had a good answer for you. It's Giphy.com. The cartoons, the cartoons are just like cartoons for dorks. I forget what their website is, but I love it. I always steal it from a friend.
Giphy.com.
Giphy has all the GIFs you could ever want. It's kind of like, you know, on your cell phone, you have, yeah, it's like that, but for the internet. So you can put it on websites, you can put it in PowerPoints. Enjoy. Okay, let's do a small group practice really quickly because we have the time and I want to make sure it's really locked in. So my question for you is there a difference in the business complaints between 2015 and 2018? So again, are we running paired or independent? Independent, good. So there's the data. You already have 311 for 2015 downloaded. Here on slide 92 is 2018's data. So go ahead and download that and then run your F test. Make sure your F is larger than your F critical. Figure out whether you run equal or unequal and then do so. I'll do it up here too, and we'll come back together in a couple minutes.
Oh, the fact is higher than one. Oh, no, excuse me. Yeah. It's high, it is higher than that. Oh, I see. Yeah. So you check the applicants that you want to see if you switch the arrays. That's what I'm doing. Oh, okay. You already got it. Higher order. Yeah. Not less than awful. It's higher. So then you do. Yeah. No, if it's not too less, then there's no difference. Override. I totally know that.
No, we didn't do the variances. What did we do?
Oh, no, we started with independent samples. We did a test first, and then we wound up doing the t-test with equal variance. Yeah. Did you do something?
So at the beginning of this, I did.
Yeah, for independent samples.
Yeah, because and then that hybrid one right? And it says the T
Yeah.
Because the value.
Yeah, well, what did you get? The P for us was 0.2.
Yeah,
Oh, okay,
Yeah. When you do the t-test, the variable 1 and 2 don't need to be the same as the f-test, right? Just making sure.
I didn't understand.
The question. So Simeo was trying to figure out, are we looking at, when we do the actual t-test, are we looking at the p-value for the one tail, or are we looking at the p-value for the two tail? And so what she was asking is, if I only want to know if it's greater, can I do one tail? But it's more a question of, is it possible that there's only a greater result, or could the average also be less? So it's a question of what's possible. And so for us, if we're looking at 2015 compared to 2018, is it possible that the average is greater for 2018? Yeah. Is it possible the average is less though? That's also probable, right? Which means you need to look at the two tail. It would just be if your answer was no to one of those questions that you would look at one tail. Okay, so how are we doing? Do you want to go over the results? So for me, I ran my F test the first time and I did 2015 here. P.S. It's sometimes helpful if you just type over those variables. One thing that I think is really helpful, one, when you're doing your homework assignment, is to write out what you're thinking, like document that. So for instance, if you were to tell me what your variables were, 2015 versus 2018, that's helpful for me because then I can understand if there's an error where it happened. So I have 2015 versus 2018, and I noticed that my F is not greater than my F critical. So I wrote down here, my F is less than the F critical, which means I need to switch variable 1 and variable 2. So I reran my F test. You can see the next F test down here. Well, first of all, did anybody else do 2015 as variable 1 and 2018 as variable 2? I did. And did you get the same problem?
Yeah. Entirely different.
Why does that keep happening? But did you find that the F is
Greater than F critical.
You found it's greater than?
Yeah.
Oh, okay, interesting.
We immediately did 2018 first.
Okay, if you did 2018 first, that'll do it. But if you did 2015 first.
Really?
So I did 15 first and 18 second, but my numbers are still different than yours. I mean, it is less than F critical, so I had to redo it.
Right,
But, it's still
but the numbers are still different. I wonder what's causing that. We could figure it out, I'm sure. Mostly what I'll say to you is that as long as your reasoning makes sense, I'm not looking for the numbers to be exactly the same. I want to make sure that for these values, you highlighted all the data. That's one really important thing. And you didn't miss any values. You didn't highlight the grand total. But more than anything, I want to see if your F is smaller than your F critical, you understand that you need to switch your variables. So that's what I said. I said, I need to switch it. I ran the F test again. Here now I have 2018 as variable 1, 2015 is variable 2. And now my F is greater than my F critical. So I found that the p-value is a tiny, tiny, tiny number. E to the negative 13 was a small number. Now we're at negative 36, which is really, really minuscule. So my conclusion is the p-value is less than the alpha value, and that the variable between, or sorry, the variance between the two sets of data is unequal. So that means I need to run the t-test for unequal variance. Did everybody at least get to that conclusion? You need to run unequal variance. Great.
We had different data, so we used equal.
Okay, but
I used equal too. Yeah.
and was it because this was greater than? Okay, great. Then you're in good shape. And then when we run the t-test, so I did the 2 samples assuming unequal. I believe I did, shoot, I wish I could remember. I think I did 2018 and then 2015, but that would make a really big difference. So you would definitely want to remember what you did. I can go back and look. So I ran my t-test. I found my p-value for the 2 tail, and that's a really small number. It's less than my alpha value. And so I can conclude that there is a statistically significant difference between the means between the 2015 and 2018. Did everybody get there with the different data? Did you find a statistically significant difference between means? What was your p-value?
Well, I mean, this is the thing. I did an equal. I ran an equal.
And that's okay. What was your p-value for that one?
My p-value was 0.98.
Yeah.
Yes.
0.98.
So there is.
So that means there is no, right? That you can conclude that there is no difference in mean between the two. Now I'm dying to know what the difference is between our data sets. You're comparing business complaints and business complaints? Did I compare business complaints and business complaints?
Yeah.
Oh my God. I'm not even gonna, I'm just gonna hide what I did. I compared residential complaints and business complaints. I did it wrong. So there you go. But good to hear that your rationale is correct. There is no real difference. I would have failed my homework, even though I documented really nicely. And we've all learned here something today. Okay, great. So that was the small group practice. I think we're ready to close unless anybody has any questions for me. I'll go over the homework in just a moment, but any concluding questions? That was a really great example of make sure that you close all the other data sets if you're comparing between two. Another thing that I'll do sometimes is just copy and paste into another tab.
Easier to have it all in one place.
Yeah, sometimes it is. I'm used to 2 screens, which makes my life easier. Any other questions lingering? It's pretty straightforward once you get to the heart of what choices you need to make. When it comes to the homework, I made sure that I opened up our the assignment for this week, so you'll be able to upload. I will double check that you're able to upload multiple documents if you want to upload the Word document as well as your spreadsheet, which you should.
Oh, say that again. Oh, you think this time we'll be able to do 2 documents?
I found out how to do that. So I'll make sure it's activated.
The previous one, you could do it.
You
This
could.
one, last one, you couldn't.
You could. Okay.
Yeah, because I didn't.
Yeah. Yeah, do. Send it to me if you still have it. Just because sometimes it doesn't matter if you got all your answers correct, but if you didn't, I like to see where you went astray.
I think my last one, my problem is that, just hiding it instead of deleting it.
Yeah, that'll make a difference.
So do I need to do it? They do it.
It depends.
I could redo it. Because I think it makes a huge difference.
I would.
If you hide it, yeah.
I would. So when it comes to the homework, there's 2 parts, 3, I guess. Make it larger. So the first part is the t-test practice. So now we're looking at sanitation complaints to see if there's a difference. And these are related to how dirty the streets are. Like when people call because there's garbage or garbage hasn't been picked up, litter. So you're looking to see if there's a difference between 2015 and 2018. The methodology is exactly the same. So you'll download the 2 and do that. Here is the analysis you're supposed to do. Here are the questions to answer, and that's around the interpretation of your data that you're getting, your analysis that you're getting. And then on page 2 is correlation practice. So the question is there a correlation between the number of business complaints and the number of sanitation complaints? So here we're going to compare business complaints with sanitation complaints. I did not need to highlight that for you.
Is it you giving us double homework because there's no class next week?
Yeah, so you have 2 weeks to do it.
Oh, there's no.
That's really glad that you brought that up so people don't show up. Yeah, you're off. Don't
I
come.
said that last time and it was class.
It's this time. So you'll run the analysis, you'll interpret the results. And then there are some ratings. I have highlighted for you some key things to look at, and then feel free to look at more if it's helpful. Thank you for bringing up the fact that please don't come here next week, but I'll see you.
You've given us double homework. Is there No homework the last.
There will be, oh, there will be homework the last class.
Is it the last class this week?
So I won't see you next week. I'll see you the week after. So that's that last week in February. And we will have homework to cement the learning. What will happen is that first week in March, you'll keep coming back. I think you'll probably be in the same room. It'll just be with your qualitative instructor. And so you'll submit just like you did. I still have time to grade it. And we still have time, if you want to revise it, you still have time to do that, because the grades aren't submitted until the end of your qualitative portion.
And you qualitative, are you?
I'm not. It'll be somebody else. And I actually don't know. It's a new instructor. I don't know who it will be. I'm sure they'll be fabulous. Let me know if you have any questions. Feel free to email me.
I think we should get break the last.
What's that?
I think we should have a homework break.
A homework break? You want to boycott the homework? How will I know if you got it? We stop the recording.